shoot, hang on a second. Got all excited. Sorry. Okay. So limits. When we want to know the limit, this is how we read this. The limit as x approaches 1, we're looking for what the y value is when x is 1. What is the graph itself getting close to as the x value approaches 1? So all along here, this is where x is 1. What is the graph approaching from each side as x approaches 1? So as I get closer to where x is 1, what's the y value? 2. But notice this is a whole. That's not the actual y value. The actual y value does not exist because there is no solid circle along x equals 1. It is completely empty. Now in example 2, we have a piecewise function where I'm using the line with a hole in it, but I have a filled in circle. I actually have a y value. Now you have to be very cautious though. This is where x is 1 on the graph. The limit is what the graph is approaching from either side. So the limit is still 2 because around where x is 1, it's getting close to 2. The actual y value is this point. The actual y value is 1. So there are times, oops, this should have gone here. There are times where the limit exists, but the y value doesn't. There are times where the limit exists, the y value exists, but they are not equal. And there are times where the limit exists, the y value exists, and they are equal. So you can have a limit without having a y value. You have to be very careful. Now, these were graphs that were already done for you. Let's look at what would the limits look like by evaluating the functions. So do you know what the graph looks like for y equals x squared? It's just a parabola. So as we get to where the parabola, where x is 2, what's the y value? 4. So if there is no break in the graph, if it is continuous function, the limit is the y value. So plug the number in, just substitute 2 into the function, that's your limit. Now, if we plug the x value into the function and it causes us to have 0 in the denominator, we can't use that value because we cannot divide by 0. So then we have to evaluate the function. So first let's check to see if there is a hole. Let's recall, when is there a hole? A hole occurs in the graph if you cancel something from the top to the bottom. So see, there is a GCF in the numerator. And so once you factor the numerator, you can see you can cancel a factor of x from the numerator and the denominator. Once you cancel that out, that means there is a hole at x equals 0. So let's look at that graph. Let's consider the graph. If I plug 0, if I graph this line, 1, 2, 3, we start at 3 with a slope of 1. But when x is 0, this is where our hole occurs at. Where I canceled a factor, that's when x is 0, y is 3, that is my hole. So if this is my hole, and then I have a slope of 1, up 1 over 1, this is what the graph actually looks like. So as soon as you cancel out your factor, then you can plug in 0. The limit is 3. That's because there is a hole at the coordinate point 0, 3. So on either side of 0, we are approaching the y value of 3. All right, let's consider this one. If we plug our 3 in, once again, you get a 0 in the denominator. So we're going to factor. Notice every time I bring down the limit as x approaches 3 or whatever that value is, factor the numerator. So once again, we can cancel a factor from the top and the bottom. This time our hole occurs when x equals 3. So we could actually graph this line once again, but instead of at 0 having the hole, my hole is now at 3. So I'm going to go up 1 over 1, that's where x is 1, up 1 over 1 again, that's when x is 2, up 1 over 1 again, that's where x is 3, that's my hole. And I can see this coordinate point is 3, 6, because I can plug this 3 into what is left over to find that y value. So that's why the limit of that function is 6, because the function on each side of 3 is approaching 6. 6 from this side and 6 from this side. So when does a hole occur? When you cancel a factor from numerator and denominator. How do you find the y value? Plug in the x value into what is left over. So let's remember our rational functions. Our rational functions can be described as any function, let's say g of x divided by h of x. Basically, it's when you have a variable in the denominator that creates a rational function, anything that can be written as a ratio. So if there is a variable in the denominator, you can have a vertical asymptote. I'm also going to say you could also have a hole, so we have to be careful about that. But vertical lines which correspond to the zeros of the denominator. So whatever makes the denominator 0, vertical asymptotes are x values that create zeros in the denominator. Horizontal lines are where the graph of the function approaches as x approaches infinity or negative infinity. I would say where. Your end model behavior is what y is approaching as x. So notice these are very similar. These are very, very similar concepts. Horizontal asymptotes can determine our end model behavior. Okay, so let's look at some of these just general rational functions. The first thing I'm going to determine what x value creates a 0 in the denominator. Those are vertical asymptotes. That's where x equals 0. Now, you must have an equation. Because it's vertical, it must be x equals, and it has to be x in order for you're plugging the value in for x. Horizontal asymptote, if x approaches infinity, let's think of a really large number. 1 divided by, say, 1,000,000. 1 divided by 1,000,000 is getting extremely close to 0. And I always say if the degree of the denominator is bigger than the degree of the numerator, it will always be 0. If the degree of denominator is greater than the degree of the numerator, y equals 0 is your horizontal asymptote. Okay, so then we put in our asymptotes where x equals 0 and y equals 0. And then we have to decide where is the graph at. So I would just plug in some points. If we plug in -1 for x, I get 1 over -1, which is -1 for our y value. So -1, 1 is below. So what happens here, these two asymptotes are forcing the shape of the graph. So my horizontal asymptote says this end model behavior is getting really close to the x-axis. This vertical asymptote we cannot cross because that would create a 0 in the denominator. Then on the right side, let's choose 1. Plug 1 in for x. 1 over 1 is 1. So graph the point 1, 1. And we have this shape. Once again, this vertical asymptote, think of like a magnet. It's getting closer and closer and closer as you get, but you cannot cross it. End model behavior, we're getting closer and closer and closer to y equals 0, the larger that x gets. Because think about it, if we plug in 2, we get 1/2. If you plug in 10, we get 1/10. The y values are getting smaller and smaller and smaller and smaller. All right. So now let's consider this graph. So first let's talk about our vertical asymptote. What creates 0 in the bottom when x equals 1? Horizontal asymptote. Now, if I plug in 1,000,000 plus 2, this 2 really doesn't matter when I'm talking about really, really big numbers or really, really little numbers. Neither does this -1. So if we're left with then f of x, which is really just y, equals x over x. We call this our end model behavior pattern or our horizontal asymptote. So I'm going to graph x equals 1 here, y equals 1 here. Then we're going to plug in some points. So if this is at 1, what numbers would be good values to plug in? 0 and 2. Now I need to resurrect my function. If we plug in 0 for x, I get 2 divided by -1, which is -2. That's also my y-intercept. Notice what happens if we plug -2 in. Let's look at that next. -2 creates 0 in the numerator. That's going to be a 0y value. That's going to be my x-intercept, which really makes sense because this curve is getting closer to y equals 1, my horizontal asymptote, and I'm blocked here by my vertical asymptote of x equals 1. Now let's go to the other side of my asymptote. Let's try +2. I plug in +2, I get 4 over 1, which is 4. And then as I get bigger and bigger, the y value gets smaller and smaller, and it's going to approach 1. Okay. All right, number 3. My vertical asymptote, what value of x makes my denominator 0 when x equals -4. Horizontal asymptote. So let's look at our power function. That's the degree of the top. I'm going to just write y equals the degree of the top over the degree of the bottom. The x's cancel. Y equals 2 will be my horizontal asymptote. 1, 2, 3, 4. 1, 2. Okay. Let's get rid of this stuff. Let's make some tables. So now I'm at -4. So let's choose to the left of -4, which would be -5. When I plug -5 in, I get -10 over -1, which is +10. So here it's going to be really tall up here. So I'm going to be going closer to 2 to the left, and I'm going to be caught by the vertical asymptote as I get closer this way. Now I'm also going to plug in -3, that's to the right of my asymptote of -4. If I plug -3 in, that's -6 over +1, which is -6. So -3, -6 stays down here. What would be my x-intercept? What if I plug in, or if I plug 0 in for x, or what value of what makes 2x equal 0 is when x is 0. And so that would make sense here. So my x-intercept and my y-intercept end up being the same. So there's my graph. All right. Number 4, I didn't fix your note sheets yet. So change your equation to match mine. So the first thing we have to do is factor the denominator so we can see each value of x that creates a 0 in the denominator. So my vertical asymptote, x equals -1 from this factor, x equals +1 from this factor. My horizontal asymptote, notice the degree of the top is 0, the degree of the bottom is 2. Anytime the degree is bigger in the denominator, it will always approach y equals 0. All right, so let's look at our graph. Y equals 0, x equals -1, x equals +1. All right, so we have actually 3 regions. To the left of -1, in between -1 and 1, and to the right of +1. So to me, the easiest one, we're going to pick a few different points. Let's just look at 0 in this middle here. If I plug 0 into the equation, I get 2 over -1, which is -2. And notice if there's not an x in the numerator, it will not cross the x-axis. There will be no x-intercept because there's nothing that will make it equal 0. So what that means is I'm not going to cross the x-axis, so I'm just going to approach the asymptotes on each side. So if this is -1, this is +1, let's look at -2. So -2 squared is 4 minus 1, that's 2/3. So -2, 2/3. If my end model behavior, or my horizontal asymptote is y equals 0, and my asymptote here, it's kind of forced into this corner here. Notice when I pick a +2, everything that I pick for my negative side, when I plug in my positive, it's going to be the same thing because my x squared minus 1 will treat it the same way. So this one's over here in this little corner. Now, anytime these are just regular factors, on each side of my asymptote, one side goes up, one side goes down. One side goes down, one side goes up. They will alternate on each side of the asymptotes. Okay, so we can also talk about limits as x approaches infinity or x approaches -infinity. All right, so let's look at letter A. If f of x equals 2 minus x over 1 plus x, it's helpful to actually graph the equation first, which is why we did some practice problems earlier we have a vertical asymptote of x equals -1 because that creates a 0 in the denominator. Our horizontal asymptote, be careful here, if we consider just the degree, the power functions in the numerator and the denominator, I get -x over x, which is -1. All right, so if we put in x equals -1 and y equals -1 onto the graph, there's our asymptotes. Now we have to find the graph. I think it is always helpful to check out what value of x makes it 0 because that's our x-intercept. So when x is 2, that makes the y 0. That's an x-intercept. We plug in 2 where y value is 0. We can plug in 0 for x, and that would be 2 over 1. So that's just 2, 0, 2. That makes sense because here's our boundaries. Now, if this is at -1, we have to go to the left of -1, which would be -2. So if I plug -2, I get 2 minus -2, which is 4, over 1 minus 2, which is -1. So 4 divided by -1 is -4. So -2, -4, that would make sense because then that would be in this corner. Okay, so it says discuss the behavior. We just kind of did it backwards a little bit, but let's look at letter B. Letter B says, what is the limit as x approaches -infinity of the graph? So we're looking for the y value as x goes to the left. As x goes all the way to the left, what y value is it getting really close to? Well, it's getting really close to the asymptote, which is -1. One of the reasons we find horizontal asymptotes, it tells us the limit as x approaches -infinity. Also, what's the limit as x approaches +infinity? Well, guess what? On this side, it's going also to the value of -1. Now remember, it's not the exact y value, it's what is the graph getting really close to. Think about infinity and -infinity. Those are really far away, and the further away we get, the closer the graph gets to the asymptote. So it's what are the graphs approaching as we get close to that. Okay, so let's consider this graph. All right, first of all, what's the graph of e to the x? Let's think about that. What's the graph of 2 to the x? This is exponential growth. Remember, e is 2.71. This is also growth. The graph of e to the x looks like this, correct? What happens if there's a negative in front of it? What does that do? That flips it upside down. So instead of it going up, it's going down. Then what if it's this 3 shifts everything up 3? Here, let me shrink this. So this is negative e to the x. So what would negative e to the negative x look like? That flips it over the y-axis. So I'm going to take this graph and flip it over the y. And then what happens if I add 3 to this function? It shifts everything up 3. So it looks now like this. All right. And maybe this would be a calculator question where you can just plug the equation into your calculator and look at it. But you really need to be able to analyze what's going on. Because think of your exponential growth in general. There's an asymptote here that it's getting really close to 0. So you have to know that the plus 3 means this side's getting really close to 3. All right. Is the graph getting close to anything as I go all the way to the left? X approaches negative infinity. Just means all the way to the left. All the way to the left. So if I trace this all the way to the left, where is it going? It's going all the way down to negative infinity. All the way down. The way down here is negative infinity. All right, what is it doing as I go to the right? X goes to positive infinity just means to the right. If I trace this all the way to the right, what's it getting really close to? That asymptote of y equals 3. And that's the end.